Hello, welcome to Jumpstarting Your Team's Machine Learning Journey. My name is Reece, Technologist at Award Solutions, and I will be your host today as we go through this material, which is an Encore presentation of the material that we went through at Mobile World Congress Americas in Los Angeles in late October. It's a pleasure for me to have you here today. Couple of housekeeping things before we get started. At any point during our time together today, if you do have questions, please go into the chat and ask, and I will answer them as best as I can. You'll see the chat at the bottom of the screen. Our plan for today is to walk through why machine learning and telecom. Why now? Machine learning is not a new topic. It's been around for a few years. Why is it an important thing in telecom, and why now? What are some of the challenges for machine learning? What makes a good machine learning project? I have a lot of people come up to me on a regular basis and ask me, I've got this data and I want to build a machine learning project around this data. And I take a look at the data and I say, great, we could do that if you wanted to, or we could just pull it into Excel and use a pivot table. Machine learning would take me 6 months and the results would be bad, or I could give you answers today and it really wouldn't cost you anything at all. So what would make a good machine learning project? And then lastly, we'll talk a little bit about machine learning, deep learning, artificial intelligence, just kind of what's the relationship between those topics. Before we get started, I want to show one of my favorite pictures with respect to AI and automation. And the reason I like this picture so much is because this helps us understand what is the problem we're trying to do, kind of helps us set the stage for AI and automation. So whenever we're talking about machine learning specifically, and AI includes machine learning, and it also includes something called rules-based AI that we're not going to talk about today. But when we think about AI and machine learning, the first thing that we need to find is we need to focus on data. What is our data set that we're going to use? This is critically important. This data set has to be something that we can use to train a model and be able to take some type of predictions from. We need to learn something from it. Now, first thing, we need to be able to get this data, and sometimes that alone is quite challenging. Most telecom operators have a large amount of data that they have access to, but it's not something that's typically shared with other people. So the first thing we need to do is we need to get that data, and we're going to talk quite a bit about this data, the nature of the data, some characteristics of this data. But what do we do with the data? So what? We have the data. What we need to do then is we need to create a model. Now, what this model creation is all about is really training. I need to train this model based off of this data to be able to make a prediction. Now, depending on the problem I'm trying to solve, the accuracy can change, the relevance might change, but the properties, the principle that we're trying to talk about here of training this model based off this data doesn't change. So first we have to acquire the data. We have to clean the data. We then have to build a model and train this model based off of this data. The third thing we need to do is we need to deploy the model. And this is taking the model and putting it into practice someplace, using it in some way. Now, the way we're going to use it is we're going to have new data come in. We're then going to make a prediction based off of that new data. Great. Now, based off of that prediction, in a perfect world, what we're going to do is we'll then take some action. I don't want to just create a model that makes a prediction for the sake of making a prediction. I need some action to be taken. Now, that action may be an automated action, or that action may be something that requires human intervention. That's fine. I don't really care about either one of those. But what I need is it needed to lead to some action. Based off of this data, we think we have some type of problem with our firewall. Let's get an engineer to look at the firewall and fix that. Based off of this data, we think we've got a problem with a specific virtual piece of equipment. We're going to talk to an automation platform to have that deployed someplace else. So we have a model that we've deployed, we've got some new data that's come in, and then we have a prediction based off of that. Now, over time, we'll learn from our results, and maybe we'll retrain the model. Maybe we'll get some new data and retrain the model and get better results and better results and better results. The analogy I always like for this retraining is, if you think about the camera that's been in your smartphone for a number of generations of smartphones, and you'll notice the cameras have gotten better and better and better. We'll just take one feature, just the identifying faces, finding faces in the picture so it can do an autofocus based off of the face. Over time, that algorithm has gotten better and better and better. So we've updated the software in the phones to take advantage of that. That would be this retraining the model and redeploying the model. So there's our background. So with that being said, let's jump into a discussion about why telecom today, why automation, or why machine learning in telecom today. Well, first, outside of telecom, why machine learning? Well, one of the big pieces of that is the nature of data has changed. There's a large amount of data that is available. Maybe it's logs, maybe it's call detail records, maybe it's alarms, maybe it's network traffic, maybe it's social media, counters and KPIs, or customer support tickets. I've been in the telecom industry for almost 30 years, and during that time, the nature of the data has changed. If you go back 20 years, when I was with Nortel Networks and helped with network planning and capacity planning and helping people kind of evolve their network, back in those days, we would look at data that came from mobility switching centers, old wireline, wireless voice switches. And we would look at a fraction of the data that was available to us. I mean, we would literally pull counters and look at 4 or 5 columns in a spreadsheet, because that's all we really had the capability of handling in those days. Now what we're saying is the volume of traffic has gone up, and we need to incorporate so much more of that traffic. And some of that data is in a non-traditional form, like just text or opinion. That's where social media customer support tickets come in. So that's why we want to look at machine learning, the nature of the data. Well, on top of that, not only do we have the nature of the data, we have the speed of the analysis. We're needing to make more and more decisions on a faster and faster basis. We need to learn how to make predictions very, very quickly. I remember, this is always one of my favorite stories, is again, at Nortel Networks back in the 90s, I remember when we improved our processes so that we could go from a 24-month design cycle to an 18-month design cycle. And that was considered just crazy fast, right? I mean, us going from 24 months to 18 months was just a huge, undertaking. And now we're trying to have deployment cycles of, multiple times a day, depending on the nature of what we're trying to do. So speed has just gotten so much faster. We need to be able to make real-time decisions. And not only that, we need to have much more of the data involved in that decision. We can't wait days, weeks, months to process that data. We have to be able to make those decisions now. And one of the other challenges in our very complicated society that we live in is there's no finite set of rules that describe everything. You get into some of these advanced technologies and there's just new stuff happening all the time. And that data is changing quite rapidly. I mean, I remember back in the 2G days when we thought a high data rate in a wireless network was, 100 kilobits per second. And then someone deployed the iPhone. And then we started to see, oh, okay, we can have a huge demand. And then we started to see, okay, so now we have a lot of downlink traffic. And then someone deployed YouTube and Facebook, where we're starting to see more uplink traffic, people sending videos. And so just over time, things change. So the nature of the data has changed and the speed of the analysis. So I put those here at the top with respect to their requirements. Those are requirements. Now, one other thing that we need to look at is what are some of the enablers? Well, there's a couple of enablers that are really helping us today. One of them is we have a better set of machine learning tools and libraries. There are more and more tools available to help us do machine learning than what we've had in the past. As a matter of fact, we don't have to do all of the hard math that we did before. That's what the tool does for me. It's kind of like in the same example that we see going back in time 40 years, where 50 years, where nobody carries a slide rule around anymore, right? I still have a slide rule. That was my father's slide rule when he was in college. I've never used it. I couldn't tell you how to use a slide rule because I don't need a slide rule. When I was in college, I had calculators. Now, my son who's in college, he has graphing calculators, or we have computers that will do the same thing. So these libraries help us do so much more. We don't have to do the basic stuff. And we have a lot of libraries, be it libraries that go into a tool like Python, or just standalone tools that will do a lot of the work for us. And we'll talk about those a little bit later. The other thing we have is we have much faster hardware than we've dealt with before. One of the main motivating factors behind machine learning being so prevalent today is just that the hardware can support it. Be it a CPU getting faster and faster, graphical processing units, GPUs from NVIDIA, or new hardware. Google has created the spec for something called a TPU, a tensor processing unit. And with all three of these, what we have in common is the ability to process data, do the machine learning functions at a much, much faster pace. This is really the reason why we see machine learning as such a big topic today. Now, a little bit of an aside, but it's very much related to the topic at hand, is the intelligent edge. Now, with the intelligent edge, what we're trying to do is we're trying to move more and more services towards the edge network. And if you were part of our conversation that we had a little bit earlier on intelligent connectivity and 5G, we talked about something called a multi-access edge computing server, or MEC. Well, MEC is an example of edge computing. And the reason I bring this up now is now we need to ask the question, where does a service need to reside? I might want to put that service out here. How does that relate to AI? AI may be a component of that service, and we'll talk a little bit more about that later. The way I'm providing that service may be provided through some type of an AI algorithm. And so we're starting to move more and more applications to the edge. Excellent. Let me pause for a second. Questions, comments, thoughts at this point? Feel free to jump in the chat if you do have any questions. So I've talked about some of the positives of machine learning. I've talked about some of the value that machine learning, and I've talked about why machine learning is a prevalent thing today. But what are some of the challenges behind machine learning? Well, for simplicity, I've grouped them into three basic categories. The first category is collecting and cleaning the data. I need to have data that is able to be used for some type of machine learning algorithm. And so we'll talk a little bit about what that means. I then need to have some type of development and training environment. How am I actually going to do the training? And then lastly, and this is really the biggest concern, is how do I deploy it and how do I reuse it? Okay, so let's take a look at each of these. So if I think about this from the perspective of an end-to-end machine learning project, I can break this down into 6 key steps. And we've talked on a high level about these. Identify the sources of my data, network equipment, call detail records, social media, billing records, databases, such. I actually need to collect the data from these various sources. And those sources may be quite different. So I may have to do some additional processing to get them in sync. Now, when I pull all of this data, this is typically referred to as creating a data lake. So someone may create the data lake for me, and I could just pull that data from this data lake. Or it may be the process of creating that data lake itself. Now, I kind of missed an opportunity. I'm still kind of kicking myself for this. Here at Award Solutions, we have gone through over the last year trying to become more of a data-driven company. Well, if you're going to be more of a data-driven company, you need data. You need to have all of your data in one place. So some of my colleagues have put together some tools to pull all that data together. And we refer to it as the golden data. And I wish I would have thought about it because we don't really have that much data. It's valuable, but it's not like it's terabytes and terabytes of data. It's like a pretty complicated spreadsheet data, level of data. And so I wish I would have called it the data puddle. And so because that's kind of representative, the data puddle. And I was talking to a colleague of mine this morning, and she does our HR stuff, and she says she gets data from some of our systems, and she thinks of it more of as a data swamp because it's just she gets what she gets, and then she has to use it. So once I've gotten the data, I have to clean the data and maybe transform it into a form that my machine learning algorithms can take. This can take up to 70% of my time. This data cleaning and data transformation phase is really a very, very difficult challenge. And that's the reason they refer to this as data science, because there's so much data science piece, there's so much, a large chunk of this that it needs to be done. We then build our model, take actions, as we've already talked about. Now, let's shift gears. Where do we need to train this model? How do we train it? And that's where we want to talk about this from kind of a computing processing perspective. So there's 2 basic ways we can do it, and then we can add a third, which we will in a second. One way we can use is CPUs. These are very generally available. They're typically slower than GPUs, but they are of a lower cost than a GPU. A GPU, special purpose, it's very fast, very expensive. It's also, since it's special purpose, it can't be used for everything. And so let's kind of take a step back. What is it that we need to do in machine learning? So all machine learning really is lots of basic math. Lots of basic math. And so it's doing very large matrix multiplication. That's really what machine learning is doing. And so CPUs can do it, but it's only able to do a few interactions at the same time. So if you think about the fact I need to do millions of multiplies and additions, CPUs can only do a handful at one time. GPUs can do more in parallel. Now, CPUs can do a lot wider variety of things. A GPU can't process things the way a CPU can. But when it comes to basic math, GPUs can do phenomenal things. And I want you to think about the monitor that you're watching this on. Every pixel, there is a decision that's being made 60 times a second of what color that pixel should be. That's what the GPU is doing. And so it's able to handle a very large amount of this with respect to gaming and that kind of stuff. Very applicable for machine learning. If we think of this from a perspective of where are we getting our resources to do this work, if I'm using some type of a cloud platform, a lot of times there is a 10x cost in using GPUs. So it can be quite expensive. But my personal experience is you can have a 3x or more speed up. So then you just have to start asking the question, is it worth it? Is it worth it? Using these GPU systems. Now, we haven't talked about this as much, but if we want to take kind of this GPU concept and extend it a bit further, we've got the TPU. So TPU, it's not just special purpose, I'll say it's AI special purpose. It's designed to do AI very, very well. Super fast. Much more expensive. Because it's very single purpose. It's very single purpose. So now it comes to what's the problem we're trying to solve. So most of the AI algorithms that I've written, I can solve them on CPUs and they're very, very fast. They're very, very simplistic algorithms. No big deal. Training them is not a big deal. If I'm trying to do a lot of video or image recognition, okay, that can become more challenging. If I'm trying to do things like cancer detection or anything that has a lot of data like that, we can start to see more and more need for those GPU type scenarios. Okay, so we've talked about kind of the nature of the data. We need to get the data, we need to clean the data, and that can be very time consuming. That can be very, very difficult, but that's one of the biggest processes. Bad data is bad results, period. Second, we need to develop an environment where we're training our model. Now, training is done once. Once you've trained it, you can then deploy it and do it multiple times. So I may spend a lot of money on the training piece, but I want to minimize the money I spend on the deployment piece, because that's really where it's going to be deployed over and over and over again. So if we think about this from a deployment perspective, there are two basic philosophies to deployment. I can deploy it locally, or I can deploy it remotely. If I'm deploying it locally, what that really means is that I'm deploying it as some type of chip that's inside of a device. And let's imagine this is like a security camera. Maybe it's some type of IoT device. And I've got a chip that's specifically designed to do this artificial intelligence inference. And there's a lot of companies that are building dedicated chips for this. And the reason for that is because they want to have something that's small, power efficient, that they can deploy with the device. Advantage, this is fast, super fast. Disadvantage, it's going to have a higher cost because it's going to have that chip. And second, it's going to be slower to update. Because this is something that we're going to have to update at every device. Even if it's just software, I've got to update it in every device. And so when I think about this, I think about IoT. And let's say I've got 1 million devices that I'm trying to manage. If I have to update every one of those million, that can get quite problematic. So let's look at the other side. The other side is to deploy our AI algorithm in the cloud. And then have our IoT device, in this example, do an API call to that cloud infrastructure. So this is going to be slower, right? We're having to go to some remote device. But it's going to be cheaper and fast to update. So now we have to ask the question, what is the problem we're trying to solve? If what we're trying to do is something that's very delay sensitive, we need to go with something that's doing the AI algorithm on board. If we've got something that has a less delay constraint, then we might do something like the API call. Let me kind of give you 2 bookends, 2 extreme cases. Autonomous driving, I want the AI algorithm in the car, right? Because I don't want to wait an extra 500 milliseconds for the picture from the camera to be sent to something in the network and then the command to apply the brakes to come back. I need the AI engine to be in the car. If I'm doing a chatbot, human speech isn't that delay sensitive. If I say something, kind of think about when you're talking to those of you, Alexa, Siri, what have you, and you say, hey Siri, there's a second or two. We don't really notice that. That's where it has time to record my voice, process it, and respond. So the question really comes in is, how quickly do we need this response? Okay, so we've talked about the nature of the data. A lot of it, we need to spend a lot of time processing it and dealing with it. We talked about training our model, GPUs, TPUs, CPUs. Now we're talking about deploying our model. Now, within the telecom space, there's kind of 2 examples I can think of. One is, I may have designed some type of AI algorithm that I'm deploying internally to the network to help me manage my network. And then there's stuff I'm selling as a service. Now, one other thing that we're starting to get into as an industry is there's a lot of models already out there. Why am I building something new? Let me give you an example. Let's say what I wanted to do is I wanted some kind of a visual recognition tool. And I wanted to use it for the sake of taking drone footage and looking at cell sites to see if there's problems. So there's kind of 2 pieces to this. There's the new data. So I've got a new data set that's based off of, in this case, the drone footage. Says PH in it. Man, that's what happens when you can't spell. There we go. And then we have image recognition models. These have been around for quite a while. We have a lot of those out there. As a matter of fact, there's a lot that are in open source. So what I'd like to do is I'd like to take a image recognition model that's already been tested, it really works, it's been used by a bunch of people, and what I want to do is I want to apply my domain-specific technology, in this case, the drone footage. And I want to retrain that model so it can identify things, and then I'm going to deploy it in my environment. This is what we refer to as model reuse. And so this is something that we're starting to see as well. Why am I starting from scratch? Especially when I start doing things like chatbots and image recognition. Those are 2 really great examples. We've solved a lot of problems with respect to chatbots. Now, maybe not in your industry, So in your industry, we may need to train it. So let's take telecommunications. Somebody says, I'm having a problem with my iPhone. Okay, problem, iPhone. We can identify those. It won't connect to the network. Okay, connect to the network is a very specific telecom phrase. It has a very specific meaning in our industry. So therefore, we need to train it to say, okay, connect to the network. That's a technical support issue. So I'm going to send this to a technical support person. Why was that charge on my bill? Okay, that's a billing related question. So we'll detect it's billing and we'll send it to a billing person. So I'm not training it to understand the human speech. I'm not training it to understand English. I'm training it to understand the domain related to this particular industry. And if it was a different industry, it was retail, it was the housing industry, it was automotive industry, each of those industries would be a different set. Alignment. I need an alignment. I had my car in the shop last week, and that was one of the things I had to do is get an alignment. Well, in the automotive industry, an alignment means something very specific. I would have to teach it that. Okay? But still, we could reuse these same models. As a matter of fact, I want to say it's Watson, IBM's Watson. One of the things that IBM is doing is they're now selling Watson and the natural language processing piece as a white label product. And so if I want to have some type of a voice recognition system in a car, building it into a car, I think Maserati was building one and they were using Watson as the engine, but they weren't saying, hey, this is Watson. It wasn't like Siri and Alexa where you say, hey, Siri. It was, hey, Maserati. And they're programming it with their own trigger phrase, and they have their own specific set of commands. Okay, so we talked about why telecom. That really boiled down to the need, and we have some enablers that are available right now. We've talked about some of the challenges, getting the data, cleaning the data, having an environment to train our model, having an environment to deploy our model, and reusing someone else's stuff. Now what I want to do is I want to talk about what does it take to build a good machine learning project. We want to build a project, and what we want to do is we want to solve a problem. Is this problem I'm trying to solve a good candidate for AI? Let's see. Now, before I get into that, there's three basic types of machine learning. We have something called supervised learning, unsupervised learning, and reinforcement learning. Now, we're not going to spend a lot of time on these, but just as a point of reference, if I'm doing supervised learning, what I have is I have data plus expected output, also referred to as tagged data. The best example is I've got 10,000 pictures, 5,000 are pictures of dogs, 5,000 are pictures of cats, and they're labeled dogs and cats. There was a tutorial that I was going through recently, and it was looking at trying to build an AI algorithm based off of GitHub comments. And what it had done, what the tag was this a system problem? Was it, there's like 4 or 5 different tags that it had. So trying to say this comment really pointed to this type of problem. That's called supervised learning. Unsupervised learning is where we have data, but we don't have a tag. We don't have an expected output. And really the goal of this learning, or the goal of this type of study, is to see if we can get some type of grouping of the data. So as an example, I have pictures of cats and dogs. I've not told the computer they're cats and dogs, but I've got pictures of cats and dogs, and it's, in a perfect world, going to separate them into 2 groups, and they so happen to be cats and dogs. We don't do a lot of unsupervised learning within the telecom space. There's a few examples, but it's kind of limited. The third example that we have is reinforcement learning. And reinforcement learning is where we provide feedback based off of something. We see this a lot in robotics and actually gameplay. And actually the gameplay is the better example. So imagine I had a system that was playing a game, Super Mario. And what it did is it kind of randomly moved. And then at the end of the game, it looked at its score. Oh, I scored 40 points. Not very good. Let me try something else. And eventually it's going to learn, since it can do these things so rapidly, it can learn to optimize that score. And what we see in practice is we see systems that go through this reinforcement learning, and they learn, and they can become just the best game players in the world. We see that in a number of different scenarios. As a matter of fact, if you're interested in this, Google's DeepMind project went through earlier this year where it did a live stream of it playing StarCraft 2. Now, I'm not an expert in StarCraft 2. I've never played StarCraft 2. But that this game can play it, and they now have it being broadcast like esports in general, is kind of an amazing thing. It was kind of a, with respect to gameplay, I'll kind of one last comment. I saw an article recently that talked about the world champion of the game Go is very frustrated because he knows he will never actually be the champion anymore because a computer can always beat him. That's how good these systems have become. Okay. Within the telecom space, most of the time what we're dealing with is supervised learning. So we have our input data, we have some type of target, or we refer to as a tag, we're building a model, and we're trying to get a function to predict. So in other words, we want a function that if we're given this data here, we learn how to predict this data here. That's what we're trying to learn. That's what we're trying to learn. Okay. What makes a good model? This is the important stuff. So as you think about a project you may be working on, these are the types of problems, these are the types of criteria that we need to think about as we decide to do this machine learning based system. First thing is, we need to have a homogeneous data set. And really what this is saying is it's saying that we have a lot of samples, and those samples are representative of other data. Our data has some degree of stability. If something is going to change rapidly, that's not going to be a good example. And do we have a good enough data set to do that prediction? So my favorite example of this is always a doctor a few years ago is trying to work on early detection of breast cancer. And so this doctor has made a plea to every woman that says, when you get a mammogram, send me the results. And the reason this doctor is saying that is because the doctor needs a very large data set of both good data as well as bad data. Because we can't learn to predict the bad if we don't also have the good. So we need a very large data set. And that is a big challenge. That is a big challenge. I was talking to a couple of high school kids working on a science fair project about AI not too long ago. And that was one of the things I said, okay, you need to get a good data set so you can train this model to identify what you want. And they're like, how do I get it? I'm like, I have no idea. But if you don't have that good data set, you'll never be able to train it and get good results. So that's my number one. Two, we need something that we need to learn. We need something to predict. We need some goal for this data. What is it we're trying to get out of this data? If we don't have a good goal, it doesn't matter. We need to have something that we're trying to predict. And three, and this kind of ties into one, is we need a problem that's consistent over time. I can't have a problem that is got a short lifespan. And so if it's a problem that, like, let me give you one of my favorite examples is I would never build an AI algorithm based off 2G equipment, because my goal is to get rid of that 2G equipment. I would never, ever, ever build an AI algorithm based off of something that's super simple or something that has a lot of change to it. Because once I develop that, the nature of the data may change, and therefore my algorithm is going to get thrown away. It needs to have something that has some persistence. And so the example that we're kind of showing here is like the nature of a face. If I build an algorithm that is able to identify faces, the nature of faces aren't likely to change in the next 5 years. So what is the problem we're trying to solve? These are things that make a good model. My biggest concern is really that source of the data. We need to have a high data volume. We need to have a high data diversity. We need to be able to clean the data. And what we mean by cleaning the data is not fixing problems we don't want to see. It's not manipulating the data. It's not changing the data so that I get the outcome I want. It's cleaning it so I'm able to use it, getting rid of data that doesn't exist, data that had some erroneous value in it. And it needs to have labels or tags. This is one of my biggest concerns, is this part right here. How do I tag the data? Well, it's a human being getting involved and saying, oh, this data sample, it means problem. Oh, that data sample, that doesn't mean problem. Because if we've not done that, we can't learn how to predict that. We've already talked a little bit about this, deploying our model with the intention of having some action. We need to be able to take some type of action. Maybe it needs to go to a human and a human can get involved. Maybe it's going to do some automated thing. So one of the examples that comes up a lot in kind of use cases of this is things like, I want an AI algorithm to take customer complaints, and then the algorithm schedule my technicians to go out. And that scheduling can be based off of where the technician's located, as well as what that technician may be capable of fixing or not capable of fixing. And with more experience, we'll get better and better algorithms. When it comes to things like IoT, we need things like machine learning just so that we can take this large quantity of data and perform something useful with it. So IoT has a ton of data that it's producing, and machine learning can help us learn from that and then do the right thing. Now, one of the things that I think is important is, as we think about processing data, there's two approaches. We've been focusing really on this bottom portion of this chart. But notice the overlap with just basic automation. Most of the data cleaning piece is common. So one of the things we're guiding a lot of our customers is to say, start with what you have now. Maybe all you want to do is, instead of manually logging onto a bunch of equipment and building a spreadsheet, you have a piece of Python code that does that for you. You save some time. Now, once you've learned that skill, once you've learned the skill of doing that basic automation, we can then modify that code to maybe do some machine learning as well. Let me pause for a second. Questions, comments, thoughts at this point? All right, cool. Let's talk a little bit about some AI concepts. And really the next couple of slides is really to lead us to kind of our conclusionary slide that I want us to talk about. We've already talked a little bit about this. Our focus so far today has been on machine learning. I haven't talked about deep learning today, but it's really a subset. What's not machine learning is something called rules-based. And we're not going to focus on that. That's an older technique. It's really not been a primary focus. It's still being looked at in some, but it's not really been a primary focus for the last decade or so. We're focused on machine learning. And that's where we need that data, and we're learning something from that data. Machine learning is creating algorithms from data that improve. Machines creating algorithms from data and improve their behavior. And really the thing that's important is I'm learning from the data. I need data so I can learn. A neural network is a way that we use to help us do some math. And our definition of simulating brain function to help computers learn, this is true, but I don't want us to get too hung up in the brain piece. Unfortunately, the legacy of artificial intelligence, we still kind of think of it from a brain perspective. I want us to think of it more as just doing some math. And this neural network helps us do that math. So when I talk about building a model, training a model, what I'm really doing is I'm really building something like you see on the screen. And then I'm trying to learn, how do I do some math? So when I have this input, the math points me to this particular output. All deep learning is really doing the same thing as machine learning with just more layers. So kind of my analogy that I like for this. And you can envision just levels of complexity. If I were to say, I want to build an algorithm that takes pictures and can tell the difference between cats and dogs. Okay, that's a level of complexity. We get that. Now I want to build a new algorithm that what it does is it determines the breed of the dog. Okay, now what I've done is I've increased the difficulty of this challenge because now I need to look at more information. I need to process more data to figure that out. Cat versus dog is pretty simple. Specific breeds of dog could be quite challenging. And then the next layer of detail would be not just the breed of dog, the specific dog. I want to come up with an algorithm that allows me to look at security camera footage and find a particular dog. Not a particular, not all dachshunds, a particular dog. And so that's really the purpose of deep learning, is to say we can have more complexity, a deeper level of complexity. Now, all of that was really to get to this slide. And this is the slide I want us to conclude on, because this is something a lot of people miss. I want us to think about building an application that uses machine learning. I don't really care what the application is. A lot of people get hung up on the machine learning piece. And we actually, me and one of my colleagues over the last couple of days, we had a conversation with a company that made a big deal about saying that they were an AI company or a machine learning company. And so we kept asking, what's machine learning about it? So that's kind of what I want you to think about as we go through this. So let's think about the fact we want to build an application. Well, the first thing we need to do is we need to somehow get into our application some input data. Maybe it's through a GUI, maybe it's through a website, maybe it's through a command line interface, but I have some application, some data that I need to enter. This is that new prediction. I'll need to clean that data in some way. If I'm entering demographic data and I have male versus female, I need to convert that to numbers. If I'm including an age of the person, I might want to put that into a bucket. I don't want 42 or 97 or 13. I want, from 0 to 18 and 19 to 35 and so on. Whatever my data cleaning strategy is. I then need to build my real program logic. And at some point in that program logic, what I'm going to end up doing is I'm going to need to make that query to that trained AI model here. So I have some new data, and I get as a response, I'll say it this way, new data, response, a new prediction. And then I'm going to take that and either provide an output or have some type of an automated action. So let's say I've developed a model that takes input of a subscriber and says, do we think the subscriber is going to churn or not? Okay, so I'm going to read in, let's just say for the sake of argument, I'm going to read in a spreadsheet with all of these subscribers, 100,000 subscribers. I'm going to clean that data, and for each subscriber, I'm going to send the characteristics of that subscriber over to my trained model, and I'm going to get a churn or no churn response. And let's just say, for the sake of this simplistic example, what I then do is I then automatically generate some type of a marketing, actually we won't say marketing, we'll say we're going to send all of the churn subscribers, we're going to send a subset of this spreadsheet, just the churn subscribers, to our customer retention department, who will then make phone calls. They may offer some type of a discount. They may do something to try to encourage this customer to stay. And since we are good programmers, we're also going to do things like have logging to make sure that if we have any problems, we're reporting those logs. We're going to have patch management. We're going to do all of that good, normal programming stuff. Now, the reason I'm going through this, the reason I wanted you to see this is what percentage of my development is really the AI algorithm? Just this part here. It's a fairly small piece. And that, I think, is a very important message. It took me a long time to kind of internalize this, is saying AI is a piece of a service. AI isn't the service. Now, a lot of services couldn't be provided without AI, but AI is just a piece of the service. Cool. Questions, comments, thoughts as we wrap up our time together today? Well, I hope this was valuable. Some key things I hope you take away from our time together today. There are many reasons for machine learning now. Nature of data, as well as the need for decisions to come at a very rapid speed, as well as some of the enablers. Some key challenges in building a machine learning model are collecting and cleaning data, a development environment, a training environment, as well as just the ability to deploy a model and then reuse other people's models. And then lastly, trained machine learning models are a key part of an application, but they're not the only part. We need to be able to input the data. We need to have processing logic. We need outputting logic, as well as management logic. Well, guys, thank you so much for your time today. Thank you for being here with me for the last hour. If you do have any questions, please feel free to reach out to me. Probably the easiest way to contact me is through LinkedIn. You can find me, Chris Reece, Ward Solutions. I'm the only one there in LinkedIn. Feel free to reach out to me. Other than that, thank you guys so much. If you get a chance to come to Barcelona, I'll be there. Come find me and say hi. Until next time, thank you so much.